This screencast is about entropy. We are going to consider entropy with state changes. We're going to look at it in the context of chemical reactions. And we're going to move on to that in terms of calculating delta S for different chemical reactions. So here is a diagram you probably saw when you were at school that has the different states of matter: solid, liquid and gas. And let's consider entropy in its most basic form as a measure of disorder of a system. Now, it should be apparent from the diagrams that as you move from a solid to a liquid to a gas, you get more disorder. So here in the solid, we've got a very regular structure. All the particles are touching each other in a very regular formation. In terms of the movement of those particles, there is some vibration around a fixed point, but overall it's very ordered. As we provide heat and we move towards the liquid phase, we begin to start to weaken the forces of attraction between the particles. So these particles can now kind of roll over each other, but they're still touching. There are not gaps here, but they are able to move over each other, which means that a liquid can flow. So we've got a bit more disorder there. And then when we move to the gas, we completely break free of the attractive forces between the molecules or particles. I say break free. We know in the context of gases that there will still be attractive forces there, but the bonds that are keeping them together in the liquid are overcome to such an extent that the particles can be completely separated from each other. If we were to draw a little graph of the temperature versus S, then you would be able to see that the disorder is going to increase, but it doesn't always increase by the same amount. So I'm going to start here. It's not necessarily going to be zero entropy because it would be difficult to have completely zero entropy. We're going to start here. So I'm going to start heating up a solid. Okay, so I'm heating up my solid and the disorder is increasing as we get more and more vibration. And then we're going to hit the melting point, at which point we'll get a fairly straight up line. So we'll get a big increase in disorder here compared to just the previous one. So now we've gone from a solid to a liquid. We're going to increase the temperature of our liquid. So again, we're going to get more vibration and we're going to increase the movement and they're going to be rolling over each other more. And then we're going to hit the boiling point. So we're going to get a really big increase in disorder as we are able to overcome the forces of attraction between the particles. So these diagrams, this is a small, that's a snail, small-ish delta S here, big delta S here. So in melting, we get the delta S there, and in boiling, we get a big change in delta S. So if you are comparing a state change in terms of entropy, then if you are moving up the state changes from solid to liquid to gas, then you've got an increase in entropy. If you're going the other way, so if you were condensing or freezing, then you would get a negative entropy change. But then if we go back that way, it's negative. So it's possible to estimate the entropy change for chemical reactions just by examining their balanced symbol equations. And we find delta S in terms of the sign. We're not able to make an estimation of how big the number will be, just whether it will be positive or negative. So we're going to examine these three chemical reactions that I've given you examples of to see if we can estimate whether they're positive or negative. The things we need to look for is how many moles of reactants and products there are. Smaller numbers of moles are less disordered than larger numbers of moles. And we also need to look at the state of phase of the reactants and products. So let's look at equation 1, and this is the burning of methane. So on the left hand side we've got 3 moles of particles, and on the right hand side we've got 3 moles of particles. So far they're even. However, when we examine the states of these, on the left everything is a gas, so very disordered. But on the right we've got 1 mole of gas but 2 moles of liquid. So that must mean that in this case the delta S is going to be negative, as the gases on the left are going to be more disordered than the gas and the liquid that's produced in the products. Looking at equation 2, here we've got 1 mole of liquid glucose, and it's making 2 moles plus 2 moles, so it's making 4 moles, and those moles of substance are aqueous and liquid. So we can estimate here that delta S is going to be positive. Finally, in equation 3, we've got the formation of PCl5, everything in the gas phase. So we have 2 moles of gas on the left and 1 mole of gas on the right. So 2 moles of a gas is going to be more disordered than 1 mole of a gas. So as we go through the reaction, we're going to have a decrease in entropy, and delta S is going to be negative. Another question you could be asked is to calculate the entropy change for a particular reaction. So you might get a table of data which has S values for some substances. And overall, you just need to remember that the change in entropy is equal to the sum of the S of the products take away the sum of the S of the reactants. All you need to do is to do that calculation, and you will be able to get a value for delta S. And just remember that the units for these are in joules per Kelvin per mole, or sometimes joules per Kelvin if you're not dealing with moles there. So remember that if you are then going to use this delta S value in a different equation where you are combining it with delta H, which will be in kilojoules per mole. Going to have a look at an example of this on the next slide. Just going to leave this equation here for a moment, and that's to give you the chance to have a go at this for yourself and to check that you understand what was on the previous slide. So here is the data for the S values for the reactants and the products in the burning of methane. So try and calculate delta S and then pause the video, and you can then compare that with my answer, and I'll go through it in a moment. So now let's carry out this calculation. So we're going to use the equation that was on the previous slide. Delta S is equal to the sum of S of the products take away the sum of S of the reactants. So we're going to set all this up. Here are my products. So I'm going to have 214 plus 2 times 69.9, take away 186 plus 2 times 205. So when we plugged all that into our calculator, we end up with minus 242.2 joules per Kelvin per mole. So again, we need to do our kind of common sense check here. Is this a sensible number? Moreover, is it a sensible sign? So it's negative, and if you remember from our previous example, if I put the states in here, we were moving from 3 moles of gas. We were keeping 3 moles, but 2 of those moles were liquid. So we had estimated just from examining the chemical equation that we would get a negative entropy change, and we have done through the calculation. So that's just a good common sense check that what you've put into your equation has come out with a sensible answer, and in this case it has. So hopefully you had a go at that for yourself, and that's the number that you got and the sign that you got, and you can be fairly confident that you are able to calculate delta S values.